Okay, and we're set. Okay, so last time we finished talking about protecting groups, right? We had group one, group two, group one, followed an SN2 mechanism, which flipped the stereochemistry, and then group two, that's the one that preserved the stereochemistry. Okay, so let's just double check our knowledge in here. So we know that basically protecting groups, they're just swapping the OH for something else that has a pretty good leaving group. So that's why in this case, PBr3, we know this guy is from group one, which is why we flip the stereochemistry, right? Okay, now I have my pretty good leaving group. Now I presented with sodium hydroxide. What's that? What kind of reagent is that? It's a base. What else? We said it was a base, but it's also a nucleophile. So if you have a nucleophile plus a carbon chain with a good leaving group, what kind of reaction are you doing? SN2, beautiful. So we know that sodium goes away, and then our hydroxide does the backside attack, which means that we flip the stereochemistry once again. So overall, from the first to the last product, did we retain or did we change the stereochemistry? We retained it. Now, what would happen if I were to use something from group two? Overall, I first start by just replacing my hydrogen for either mesylate or tosylate, whatever protecting group you're given. And then we retain the stereochemistry so far. But if we want to do an SN2 reaction afterwards, remember, same process. Hydroxide does the backside attack, meaning that you're going to flip the stereochemistry. So overall, is it retained or flipped? Whoa, it's flipped. So overall, it's inverted. So yeah, basically, this is just a review of what we covered last time. So questions on protecting groups. They're pretty simple. As long as you're able to memorize the different lists, you should be good. And then let's check a problem that you might encounter. Okay, so in this case, you're given two reactions and you're given a different set of reagents. So for the first transformation, when we're keeping the same stereochemistry overall, which of those reactions would I do? A or B? Whoa, A or B? It's gonna be B because remember, this guy was the one that flipped the stereochemistry first. But then if we do an SN2 reaction once again, we flip it, so we retain the overall stereochemistry. So process of elimination, this guy is just gonna be A. Okay, questions so far on that? Again, this is just a review. Should be relatively easy. Are you good? Okay. Now, let's start talking about our dear oxidation. But before that, how do we know we're doing a reduction? Reductions was the decrease of bonds between carbon and oxygen. So oxidation is just the complete opposite. When you increase the amount of bonds between carbon and oxygen. So that means going from an alcohol to a carbonyl group. Now for oxidations, you only have to know three main transformations. Now let's start with the very first one. In this case, that alcohol group, is it primary or secondary? Primary. Okay. Whenever you start with a primary alcohol and you end up with a carboxylic acid, that means that you used a strong oxidizing agent. Okay. So again, you start with a primary alcohol, you end with a carboxylic acid. That means that you used a strong oxidizing agent. Now, if we start with the same exact molecule, primary alcohol, but this time we end up with, what's the name of that functional group? With an aldehyde, then that means that we technically stopped at intermediate. So we used something that was weak. Then very last one. With a secondary alcohol, this one's different. But no matter what kind of reagent you use, strong or weak, you're always gonna end up with a ketone. Okay, so those are the three main transformations that you have to remember. Again, primary, if I react with a strong one, I create a carboxylic acid. But if I react with a weak one, I end up with my aldehyde. For secondary alcohols, I'm always gonna end up with a ketone. Okay, so far, questions on that? We're good, it makes sense. So again, this part is mainly just memorizing. The mechanism for oxidations, they can be a little bit lengthy. You don't really have to worry about. Maybe your professors are gonna show it in lecture, but try not to get confused. Again, you only wanna notice the first molecule and final product, that's it. So now that we know basically the shortcuts, we need to know the different reagents. So for oxidation, there's more than two. So it's gonna be a bit of memorizing, but I would recommend you to just memorize the weak ones that are PCC and Swern's reagent. Now for Dr. Roche usually just calls this entire thing Swern's reagent. But Dr. West, he's actually gonna give you that full thing on your arrow. So keep that in mind. He's not gonna give you the name. Dr. Roche prefers to use the names. But again, just remember PCC and DMSO. Those are going to be your weak oxidizing agents. Those are the easiest to memorize. Now, for the strong ones, yes, you can memorize those four of them, but you can also notice that all of them have a high content of oxygen. So that's going to be your main clue to figure out that they are a strong oxidizing agent. Okay. So I'm just going to give you one more minute to finish writing down your notes for this. Again, very important for you to start memorizing that list. Okay, so far we're good. Okay, again, what was the definition of oxidation? The increase of bonds between carbon and oxygen, so reduction is the complete opposite. Okay, now, at this point, we're not even halfway done with the handout. So as you probably noticed, there's a lot of reagents for chapter 11 and 12. So I know that you just took your first exam, but I highly encourage you to start making a list of reagents for every single one that you see, okay? So just start your list and keep adding reagents as we move on through the chapter, okay? Because it's gonna get to a point where you might get a little overwhelmed. Again, chapter 11 and 12, they tend to be a little bit lengthy. So please start early with that list of reagents, okay? That's just my recommendation. For Dr. West, your exam is at the end of this month, I think, right? Yeah, 28th, yeah, one of those. I think he's gonna go into 13, possibly 14. So yeah. So yeah, after he spent a while on chapter 9, he tends to go a little bit faster for the next few chapters. So yeah, get ready. Again, start early, please. Don't wait until last minute because you're gonna get overwhelmed. But either way, oxidation, basically, this is wrapping up our discussion with reactions with alcohol groups. Now we're gonna start talking about our ethers. Now, let's start with the very first reaction, which is called your Williamson ether synthesis. Now, that's a bit lengthy again. So I just like to call this your Dear West reaction, which kind of sounds like your professor, but without the T. Okay, this is going to be your West reaction. This is when we start making our Dear ethers. Okay, now, West reaction, that's a new reaction for you guys, but technically you already know it because it contains two basic steps, the first one and the second one. Now, first one is really easy. It's your acid-base reaction, which is something that we're really used to it. We just take away a hydrogen, that's it. Now, if we take away a hydrogen, that means that you're creating the conjugate base or a pretty good nucleophile. Nucleophile, in this chapter, we've seen that SN2 reactions come back, so second step is just SN2. Simple as that. You're familiar with both reactions, so you're just combining them to make your West reaction. That's it. Now, let's start with our dear alcohol group and sodium hydroxide. But let's practice IUPAC. What's the name of that alcohol group? It's ethanol, exactly. We just have two carbons. And then again, OL just represents your alcohol group. Now, NaOH, what is that? What kind of reagent? Is it an acid? It's a base. Okay, so let's start identifying main reagents. Again, you can add this to your list. Main reagents for West, at least for the first portion, is that you need some sort of base. Usually it's just going to be sodium hydroxide, or it can also be this guy in here. Because remember, at the end, ionic bonds, they go away, and we're actually left with the active base. Now, also, next main reagent for your West reaction is that you need some sort of alcohol group. And yes, it's always going to be an alcohol group. Okay. So earlier in this chapter, we were talking about how alcohol groups can be acids. So our alcohol is our acid. We're given sodium hydroxide as our base. So we know that we're just going to be abstracting that hydrogen and creating the deprotonated version of the alcohol. Now, how do we call the conjugate base of alcohols? We talked about this before. Alkoxide, exactly. Now, more specifically, because we have two carbon chains, this one is going to be ethoxide. Okay, again, first step, we just did it. Acid-base reaction, that's it. Simple as that. Now, because of that, we just created a pretty good nucleophile. So next main step in this reaction is going to be an alkyl halide or something with a pretty good leaving group. So if we know that it's SN2, this oxygen does the backside attack and kicks out your leaving group. And now just for the sake of this, let's show stereochemistry. So let's say that our alcohol started out with a wedge. So our ethoxide still has a little wedge. And then let's say that our alkyl halide had a dash. Okay. And again, this guy is just your alkyl halide. Simple as that. So we know that the first bond to that oxygen, it came from the alcohol, so that stays the same. That's still on a wedge. But now this carbon is going to flip the stereochemistry. So now instead of having a dash, we have two wedges in there. Again, this is carbon 1, carbon 2, 1 and 2. So you can keep track of everything. So far, questions on that? Pretty simple? Yes. I added the dash just for the sake of explaining what happens to the stereochemistry, because it just started out as planar. So yeah, just add that to your handout. Okay, so far, any other questions? Relatively simple? Okay. Now, we're going to be talking more about IUPAC for ethers, but just for now, ethers tend to be pretty easy to be named, especially whenever you see that the carbon chains connected to the oxygen are the same exact thing. So first of all, your parent chain is literally just going to be ether. Simple as that. It's just going to be ether. And then you just have to name your carbon chains. So in this case, we have two carbon chains. So that means that it's ethyl. But we have two of the same, so diethyl. So full name, diethyl ether. Simple as that. We're going to see how it can get more complicated on Monday. So don't worry about it for now. So far, questions on that? We good? Okay, now, as you saw, your West reaction creates an ether. Now, sometimes you can make an intermolecular reaction, meaning that you're creating a cyclic ether. Now, specifically, we're going to be focusing on this little guy in here. The one that looks like a little triangle. Do you guys know the common name for that one? I'm not sure if you already mentioned that in lecture. Yes. Similar. It's actually an epoxide. So again, main focus of this chapter is going to be a special kind of ethers, which is going to be your epoxides. Those guys, later on, we're going to see how they're very reactive. But any guesses on why they would be so reactive? Yes. Beautiful, exactly. There's a lot of ring strain in here. So that makes it really unstable, therefore more reactive. Okay, now, Let's see how our West reaction is going to play out whenever you're given everything within the same molecule. Now, again, I know I'm doing this reaction. Why? Because I'm provided with a base, I see an alcohol group, and a pretty good leaving group. Whenever you have those three factors combined, you're always doing your West reaction. Okay, so this time you guys are going to walk me through the mechanism. So what's going to happen first? Which lone pair? Sodium goes away. I'm left with the active base. Takes it away so I can create my alkoxide. So I'm going to have still my halogen. Okay, I'm at this point. Now what happens? Is that it? That's my product? The alkoxide? Beautiful, exactly. If we already did the acid-base reaction, we need to do SN2. So lone pairs do the backside attack and kick out your leaving group. Remember, this is SN2, so it means that we flip the stereochemistry. Now for this one, I'm gonna show you the little transition state so we keep track of everything. But basically, remember, I'm making a new bond to this carbon and I'm breaking the bond between carbon and halogen. So again, this is technically your transition state. So at the end, the bonds are going to get rearranged. So we create this guy in here, or the epoxide. It needs to go down so there's not too much steric hindrance in the molecule. So it's going to rearrange itself. So technically, it's going to start looking like this first. We still have this guy. Once we make the new bond, it's right there, but there's a lot of ring strain, there's a lot of steric hindrance in the molecule. So this bond is going to start rotating to liberate some of that steric hindrance. So it's more stable. And then that's how we end up with their normal epoxide. Okay, so far, questions on the intermolecular West reaction? Yes. Yes. Let me bring out the pointer for this one. Okay, so again, once we already formed the alkoxide, we need to do our SN2 reaction. Okay, so lone pairs in the oxygen, do the backside attack, get connected to this carbon, and kick out your halogen. So far in your transition state, that's why everything is basically just dashed, because this first bond is representing the new one that you're forming. Next one, it's the bond that you're breaking. Again, this is a transition state. This is showing what's happening in between. But after that, we know that we finally finalized our new connection in here. But there's a lot of steric hindrance. So to relieve some of that, I'm gonna rotate the single bond downwards. Okay. And yes. Okay. Technically, yes, but everything is happening within the transition state. The only reason why I'm showing it like that is so everyone can keep track of everything and why it's happening. Okay, so far, any other questions on the West reaction? Again, you need three main components: alcohol, base, leaving group. That's it. Now, this is one of the ways in which you're going to make your ethers. Now, let's talk about how to break them. So first of all, this one is going to apply for any ethers. They can be linear or they can be cyclic. It's going to apply for everything but epoxides. Okay, we're not talking about epoxides yet. Epoxides are going to be something different. Now, your cyclic ether specifically, those guys are gonna be cleaved only in acids. They're only reactive in acids. Okay, which means that if you're given a cyclic ether and a base, nothing is gonna happen. Okay, so again, they're only reactive in acids. And they're stable in your dear bases. Okay, now, before I show you the actual mechanism, I'm gonna give you a specific ranking. This ranking is gonna be to look at the carbons directly connected to the oxygen. The ranking is gonna be as it follows: tertiary, then primary, and then secondary. Now, hold on. This specific ranking is specifically for Dr. West. For Dr. Roche, it's going to be slightly different in acids. It's going to be tertiary, then secondary, and then, whoops, that's wrong, primary. Yeah. So yeah, they do disagree on that. So yes, I already talked with your professor last semester. I explained that Dr. Roche doesn't agree with his ranking, and apparently it's because they got different results during lab. So that's why they're following different rankings. It's based on what they saw in their research. So besides that, I have no idea how to explain it. So we're just gonna take it as it is. If you take it Dr. West, 3-1-2. If you take Dr. Roche, 3-2-1. Simple as that. Okay, so just focus on your rankings based on your professor. You can ask them actually the actual reasoning behind it. I don't know if they are gonna agree at some point, but yeah. Okay. Yes. So a cyclic ether is going to be any rings that have an ether, of course, but that have more than 2 carbons. So 3 carbons and above. If it only has 2 carbons, that's an epoxide. Okay. Yes. Yes. Your epoxide is always the one that's a triangle. Simple as that. If you see any other shapes, square and above, that's just a normal cyclic ether. But either way, let's start looking at how to cleave or their ethers in here. So first of all, whenever we're cleaving something, that means that we're breaking open a carbon chain. Specifically, if we start with a cyclic ether, we're not going to have something cyclic at the end. Everything is going to be linear. So that means that at the end, your oxygen needs to be some sort of leaving group. But oxygen, as it is right now, is not a pretty good leaving group. So how can we make it better? Protonating it, exactly. So first step is always going to be your simple acid-base reaction. This oxygen is going to grab the hydrogen from your acid. So now we can have OH as the leaving group. And of course, now that oxygen is going to have a positive charge because it has 3 bonds. Okay, now, after we have our pretty good leaving group, now we can start looking at the ranking. So to do that again, I'm just looking at the carbons directly connected to the oxygen. And then I'm just going to look at the degrees of each one of them. So we're going to start with the one at the bottom. And little disclaimer, bonds to oxygen do not count as R groups. So for the one at the bottom, what's the degree? It's just primary. We only have one connection. What about the one on top? Secondary, beautiful. Okay, now, how many Dr. Roche students do I have right now? Just one? Okay, so I'm gonna show the 2 different products just for your sake, so you don't get confused, but let's separate this. This is gonna be your Dr. West cleaving, and this is gonna be your Dr. Roche's cleaving. So yeah, just so everyone gets it, just again, just focus on your professor. So yeah, it's a little silly, but yeah, it makes the job a little harder, but either way. So if we're following Dr. West's ranking, what am I gonna prefer to cleave, the primary or the secondary one? The primary one. So I'm gonna be breaking open this carbon chain from here. And again, since it's cyclic, you have to keep track of every single carbon. So I'm just gonna start labeling. Again, there's no specific number. There's no specific order to number your carbons in here. Okay, it doesn't really matter. It's just to keep track of them. So let's see. This guy is gonna start by having little carbocation. OH. And then we have now, remember, since I'm cleaving open that bond between the primary carbon and the oxygen, now my primary carbon is lacking a bond. That's why there's a little carbocation there. Okay, I'm just lacking a bond. Now, so far, I already have my molecule cleaved open. Everything is linear, but we have to make it a little more stable in there. So how are we going to neutralize that positive charge? Resonance? I heard it over here. How am I going to neutralize it? What can I add? Bromine. Exactly. Because remember, from the very first step, after I took away that hydrogen, technically, we're going to have bromine minus just floating around. So this guy comes back again and gets connected in there because it's going to do a little nucleophilic attack. So that's how we end up with this guy in here. And again, that's for Dr. West, just to clarify things. Okay, now let's look at what's going to happen if we were to follow Dr. Roche's ranking. So we know that Dr. Roche is going to prefer to cleave something that's secondary over something that's primary. So this time I'm cleaving open from here. So let's just do this 1, 2, 3, 4, 5, and 6. This time my oxygen is going to be hanging from carbon 1. I'm going to have OH in here. And then my carbocation is going to be on carbon 5. So far, we're good? Okay. So now, same process as before. Everything is almost perfect. We just have to neutralize that positive charge. So our bromine is just going to do the nucleophilic attack. And then we end up with this little guy. Whoops. Oxygen. Bromine. So yeah, notice how we're going to get different products depending on what professor's ranking you're following. So again, always just look at your specific one. But so far, questions on it, on the mechanism. We're good? Pretty simple to follow? Okay, now, on the next one, we're given the same exact molecule. So overall, we're going to proceed with the same exact products, but there's a difference. This time you're given your acid in excess. So whenever you're given something in excess, of course, you're going to repeat the reaction multiple times. Now, let's see how this is going to happen. But first, I'm just going to copy and paste the same mechanism. And then let's see what happens with your base. With your axis. Okay. Okay. Again, everything is going to start the same exact way, but because we have access, we're going to keep going. So at this point, I have my products, but I still have HBr floating around. Okay. Now, I know that oxygen, I can make it into a pretty good leaving group. So same process as before. We're just gonna protonate it. So this time water is gonna be our leaving group. So let's just see. Okay, so now I just have one more bond and I have a positive charge in that oxygen, which means that now it's ready to go. Okay. Now, after that, we know that we have to do some sort of nucleophilic addition. So this time, same process as before. We still have Br minus just floating around. So we know that we're gonna do a little SN2 reaction in here. So that means that we do the backside attack to carbon 5. In this case, if we're looking at Dr. Wes's ranking, and we kick out our dear water. So now we end up with this carbon chain. Now we have bromine in carbon 5. And then same process for Dr. Roche. We do our little nucleophilic attack. Whoops, that's the wrong carbon. We do our nucleophilic attack to carbon 1 this time and kick out our water. So this time we're gonna end up with the same exact product for both professors if you're given the acid and axis again. And technically, yes, your byproduct is gonna be water. Plus H2O. Okay, questions, yes. Yes, it would. Exactly. Yeah, usually both professors are just gonna give you the cleaving of ethers and just planar bonds. But if they were to show you stereochemistry, then yeah, you would flip it. Okay, questions so far? So did you guys notice a little shortcut in all of this? Are we gonna do the full mechanism on the exam? No? So what's the shortcut? What do you notice? We can start with the easy one, the one with X's. Exactly. At the end, you just want pure halogens that came from your acid for X's. But if you're not giving it an axis, as long as you know the ranking, of course, you're going to know where to cleave it. Exactly. So after that, keep in mind, wherever you cleave, that means that's where your carbocation was. Well, that's where it is going to be. But that means that your halogen is going to be there where you cleaved. And then the remaining alcohol group, that's going to be wherever the initial ether was. And that's it. So again, as long as you know where exactly you're cleaving, you're good. But yeah, if you want to do the mechanism, that's completely okay too. It's just, it might take a little bit of time. And again, remember to keep track of your carbons, please. Okay, so far, questions. We're good? Pretty simple? Okay, we're doing good? Okay, now let's start talking specifically about our dear epoxides. Okay? So first of all, we know that our epoxides are going to be very, very reactive. And this is going to apply for both acids and bases. Okay, again, this is happening because of the ring strain that we have. Okay, now, before we focus on our cleavage, we know how to make them. Now, for epoxy specifically, there's going to be two different ways. One of them, you already know it, the West reaction. The other one is going to be with reagents called peroxy acids. Okay, now your peroxy acids, there's only two kinds. The ones that you see in there for Dr. West, usually he is going to give you those guys in condensed formula, but one of them is really easy to memorize, the one on the left side. The right one, it's quite lengthy, but I want you to notice a certain pattern. CO3H. Whenever you see CO3H, that indicates that you have a peroxy acid, at least for this class. But let's just start looking at how the molecules look like in bond line. Okay, now for Dr. Roche, usually for the second peroxy acid, he either draws out the molecule with a little benzene group, or he just refers to it as MCPBA. They both mean the same exact thing. But again, your main focus is to look for CO3H. That's how you know that you have specifically a peroxy acid. I'm sorry? I'm not sure. I'm really not sure. It's the full name of the molecule, but simplified. So yeah, whenever you see MCPBA, it's just that specific peroxy acid. The full name, not sure. I just know that it starts with meta. The rest, no idea. Okay. So again, there's two main ways in which you can make your peroxy acid. So, sorry, in which you can make your epoxide. First one is going to be with your peroxy acid and a double bond. So it's going to be a double bond plus your dear peroxy acid. Now, as you probably guessed that, we don't have to worry about the mechanism. The only thing that we have to keep in mind is that this reaction is following a syn addition. So that means that bonds should be on the same plane. So let's say that we're going to start with this little alkene. Okay, simple alkene. And then I'm going to react with our CO3H. Again, CO3H, that's your main portion. That's a peroxy acid. So all you have to know is that you're going to use the pi electrons from the double bond in here to make the two new connections to the oxygen. The oxygen is coming from your peroxy acid. So in this case, I still have the same carbon chain, but no double bond. And then my bonds to the oxygen, they need to be on the same plane. They can both be wedges or they can both be dashes. Okay, and that's because it's an addition. Simple as that. That's all you have to know. Initial molecule, reagent, product. Now we know that the other way is with your intramolecular West reaction. Now, for this one, both professors like to bring back another reaction from Orgo 1, which is your halohydrin formation. This is from chapter 8. But let's just quickly review this. We don't have to do the full mechanism again. As long as you know your initial final product, you're good. So usually those guys start with an alkene. And then again, I'm doing my halohydrin formation. We are going to be using Cl2 with water at the bottom. Now, before I show you the product for this first part, what were the three main components that tell you that you're doing a West reaction. Good leaving group, base, and alcohol. Beautiful. As soon as you see those three factors, you know you're doing West. But in this case, once we do our halohydrogen formation, we know that that's just an addition reaction, so we're not going to have a double bond anymore. So let's just start drawing out the same carbon skeleton. And now specifically, this guy, it's an anti-addition, meaning that you are going to be adding a chlorine in an alcohol group, but they need to be trans to each other. So let's say that our alcohol group is on a wedge. So our chlorine needs to be on a dash. Again, that's all you need to remember. Trans addition. That's it. So we already have our alcohol and leaving group. So the only thing I'm missing is a little base. So at this point, just for an example, let's use NaH. So now this portion should look very familiar. It's what we already did at the beginning of the session. Sodium goes away. You're left with the actual base. And then what am I going to attack? The alcohol, exactly. I just want to deprotonate it so I can create my good nucleophile for my SN2 reaction. So there's my alkoxide. I still have my chlorine here. Remember, first part, this was just acid-base reaction. Then I want to do my SN2 reaction. So to do that, I use the lumpers in the oxygen. I do the backside attack, and that's how I kick out, my leaving group. Now, again, remember, it's SN2, so I need to show the change in stereochemistry. So I'm going to keep that bond on the same plane, but the one that I attacked needs to get flipped. Yes. Yes, it comes from the water. Okay, do we have any questions on this one? Yes. No, there's a specific order. I think it's Markovnikov, so yeah. The OH would go on the more substituted side, yeah. But either way, I'll double check that with my notes and then confirm it on Monday. So yeah. No, yeah, that's a good question. Yeah. Usually they provide a simple alkene, but yeah, let me just double check that for Monday. But if we don't have any more questions, you guys are more than welcome to go. Go to class. And then we'll continue with this handout on Monday. Remember, it's in GN 101. Today? Oh, yeah. Christian has to read from 12 until 2. Yeah. So you guys are more than welcome to join him at the SLC. Yes. Yes. Usually we use oxidations and multi-step synthesis. So one of the steps is going to be an oxidation. So as long as you're able to identify any of those, depending on what you start with, what kind of alcohol, you're going to know specifically what you're forming. That's it. Yeah. So yeah. And the transformation. There you go. Yes.
This week one, you would pick one of these and you know they would have to form an aldehyde. That's it.
There you go. Simple as that.